All right. Unit 9, Lesson 2 at 9:30. We're going to do some more on graphing quadratics. Yesterday, we started the process of learning what a quadratic equation looked like when we put it on the graph. We made some tables. We learned about some transformations when we add or subtract to that equation. So today we're going to continue on. We're going to talk about what happens when we multiply different things to our quadratic equation. So remember that the most basic quadratic equation that you can possibly have is just y equals x squared, or f of x equals x squared. And that's what we call our parent function. So on our graph here, we have that parent function already drawn in for us, just like yesterday. And what we're going to try and figure out this time is what happens when I multiply that basic equation by -1. So if you notice here, our g of x, our new function, is going to be g of x equals -x squared, or -1 times x squared, right? So in this first one, that would be -1 times -3 squared, or -1 times 9, which would give us -9, right? So my first point would be at -3, comma, -9. -3, -9, all the way down here. Let's see, then I'm going to have -1 times -2 squared. So that'd be -1 times 4, which would be -4. So I've got the point at -2, -4. There's my next one. I've got -1 times -1 squared. So -1 times 1 would give me -1. So I've got a point at -1, -1. Now I've got -1 times 0 squared. -1 times 0 is just 0, so I still have a point here at the origin. So notice my vertex is not moving today when I'm multiplying my equation. So now I'm going to come back the other way. -1 times 1 squared, -1 times 1. So I'm going to have a point at +1, -1. All right, and then I'm going to have -1 times 2 squared, -1 times 4. Sorry, trying to write fast. So I would have a point at 2, comma, -4. Here. And finally, -1 times 3 squared would be -1 times 9. So that would be at 3, comma, -9. 3, -9 is here. So now if I draw in that parabola, hopefully I have plenty of points to do that. See if I can't draw that in pretty well. It's going to look something like this. So what do we notice happened when we multiplied by a negative is it flipped upside down, right? It flipped. But what's that good math vocabulary for a flip? We call this a reflection. And whenever we say it's a reflection, we had to say, what did it reflect over? And in this case, it reflected over this x-axis, right? This line right here is what it flipped over. So we would say it's a reflection over the x-axis. That's what happens when I multiply in one of my equation, my quadratic equation, by a negative number. It's a reflection over the x-axis. And that was a pretty good practice doing a table as well that wasn't too complicated. All right, so let's move down now. What if I don't multiply by a negative, but what if I multiply by 2? So again, this is the new function that I'm going to graph. My parent function, y equals x squared, or f of x equals x squared, is already on the graph for us. So let's see what happens now if I do 2 times -3 squared would be 2 times 9, which will give me 18. So I'll have a point at -3, comma, 18, -3, all the way up to 18, okay? Then I'm going to have 2 times -2 squared. So 2 times 4 would give me 8. So I've got a point at -2, comma, 8. -2, 8 would be right here. There we go. And I've got 2 times -1 squared. 2 times 1, which is 2. So I've got a point at negative 1 comma 2. Negative 1, 2. Wow, we're really dropping fast here. Now I've got 2 times 0 squared. 2 times 0 is just 0. So I've got my point at the origin. So again here, my vertex is not moving. It is staying put when I'm multiplying. So now I'm going to come back the other way. I've got 2 times 1 squared. 2 times 1 is 2. So I've got a point at 1 comma 2. All right. And I've got 2 times 2 squared, which would be 2 times 4, which is 8. So I've got a point at 2 comma 8. 8. And then last one here, I've got 2 times 3 squared, which would be 2 times 9 at 18. So I have a point at 3 comma 18. 3, 18. Right up here. So again here, if I graph that line, or that parabola, excuse me, not a line, oh my goodness. Graph my parabola. Wow, look at that. Now, my vertex stayed the same, right? Right down here. Sorry if I didn't quite meet, but that would be the idea. So what happened to my graph here? It didn't move left, right, up, or down because my vertex is in the same spot. It did not flip over. That one was an easy one to see. What happened is it got narrower, right? My graph is definitely skinnier than it was before. That's kind of how we think of it, as it's getting narrower. It's getting closer to that axis of symmetry. But it does have a technical name when our graph gets narrower like that. And this is what gets a little bit complicated. So when we are looking at these transformations for our parabolas, notice in the last one when I was reflecting, I reflected over the x-axis. As you're going to see later on, the x-axis is extremely important when we're talking about parabolas. It gives us solutions and a whole bunch of things. So we're always referencing this x-axis. So as we notice on this one, my original parabola was in black there, and my new one is in teal. And that teal one pulled farther away from the x-axis, right? It pushed itself away from the x-axis. It's pulling away from the x-axis. So we, in fact, call this a vertical stretch. It's stretching away from the x-axis. Stretch. Even though it's getting narrower, we call it a stretch because it's pulling itself away from the x-axis. A little counterintuitive, so that's one that you're definitely going to want to write down and really think about. So whenever we say that, it's a vertical stretch or whatever the transformation is, we always want to say by how much. So in this case, it's a vertical stretch by a factor of 2. I was multiplying by 2, so it's stretching by a factor of 2. All right. So, maybe we'll want to add this in pulling away. All right, so we've got an idea by making all these tables we can kind of see, but my goodness, we don't want to make a table every single time, right? So instead of making a table every single time, we're going to try and find the pattern, right? So we're going to do a couple of these. And after we kind of look through them, what we're going to do is we're going to look at it, and then I'm going to show you the Desmos. Desmos is a graphing calculator where it can quickly graph our equations for us. And that Desmos program will show us exactly what our graph is going to look like. And then we'll copy it over here and write down what we can say happens when we multiply by different terms here. So when I look at my new equation here, my new equation is going to be g of x equals 3x squared. So again, my original f of x is graphed for me right there. So g of x is going to be multiplying by 3, right? This number that we multiply by, I probably should have said that back here. The number that we multiply by, we call this a. So in this case, a equals -1. Ax squared, whatever you're multiplying by. It's going to come up later on when we get to our different forms. So in this case, a equals 2, and that's where we're getting our factor of 2, right? So on our new one here, we're going to multiply by 3. So in this one, I have a equals 3. So what do we think is going to happen when I multiply by 3? We just saw what happened when I multiplied by 2. So let's see what happens when I multiply by 3. So here is, I'm going to switch over really quick. Okay, so f of x equals x squared. There's my original, right? So now my new one, g of x equals 3x squared. What just happened? What just happened was I got even skinnier, right? Now notice the things that we have here. Here's my vertex still at 0, 0. But notice my first points aren't up 1 and over 1. Notice my first points are going way up here, right? And way up here. That's 2, I guess. But that's the idea here, is that at over 1, I'm not just going up 1, I'm going way up, right? So that's why we have our scale is set a little bit different. But these points right here would be at 3, 3, and 3, right? Right there, pretty close. So when I multiply by 3, I'm actually getting skinnier by a factor of 3. So I'm going to come back over onto my notes, and I'm going to say, all right, so what did we sketch here? We saw that my vertex was in the same spot, but then my next points were over 1 and up 3, and over and up 3. And this was what g of x looked like. And if we remember back, again, that is a vertical stretch by a factor of 3. And again, we call it a vertical stretch because it's in reference to this x-axis, and it is pulling away. It's stretching away from the x-axis compared to that original one. It's stretching away from it. All right, so that's what if I multiply it by 3. Now, what happens if I multiply it by 1/3? Let's flip over here to Desmos, and let's change our 3 to a 1/3. Whoa, so again, red was the original, now blue is the new one. This is multiplying by 1/3. So it didn't get skinnier this time, it actually got wider. Now, when we go over 1, we go up, 1/3, right? You can kind of see how here's the distance between 0 and 1. So that first point is going up 1/3 of the way. You could also see, okay, for it to go up to 3 like it did before, I have to go all the way over to 3 and then up 3 instead of going 1. Okay, so over 1, I go up 1/3. So if I'm going to sketch what that looked like, on this one, again, my vertex was in the same place, but when I went over 1, it only went up 1/3. So it's somewhere around here. Now I could do what I said, like over 3 and up 3 if I wanted a better point to graph. Something like this would get the idea. But that scale factor, that factor of 1/3 should really kind of give us our idea of where to make those points. So this time, in reference to my x-axis here, this time I'm not pulling away from it. I'm not stretching away, but instead I'm pushing closer to the x-axis. I'm pushing closer. So on this one, my graph is getting wider, right? But it's not a vertical stretch, but instead this is called a vertical compression. A vertical compression by a factor of 1/3. So when it gets narrower, when my graph gets narrower, like in number 2 and 3, I call it a vertical stretch because it's pulling away from that x-axis. It pulls away. So that's why we call it a stretch. On this one, it's pushing closer to that x-axis. So that's why I call it a vertical compression. All right. So how am I going to know the difference? How do I know when it's going to be a vertical stretch, if it's going to get narrower, or if it's going to be a vertical compression when it gets wider? So it all depends on that A value, right? Here, A was 1/3. So notice what people usually say is, okay, when I'm multiplying by a whole number, 2, 3, 4, that's when it's getting narrower. When I multiply by a fraction, 1/2, 1/3, that's when it's getting wider or a vertical compression. The only thing is, it's not necessarily that it's a whole number or a fraction, but it's actually that it's multiplying by a number larger or smaller than 1. So I get a vertical stretch. I get a vertical stretch, meaning that it's getting narrower when I multiply by a number larger than 1. Or in other words, A is greater than 1. I get a vertical compression, or it's getting wider when I multiply by a number less than 1. Now, less than 1 is a little bit tricky, right? Because we already learned in the first one, what happens when I multiply by a negative? When I multiply by a negative, that's when I get my reflection, right? So a reflection over the x-axis, that's when I multiply by a negative number, or A is less than 0, right? So no matter if it's a fraction or a whole number or whatever, if it's a negative number, it's going to flip over the x-axis. So really, when I say that this number is less than 1, really what I mean is without the negatives, right? Or in other words, the absolute value of that number. Ignore the negative. What's just the number part of it? If that's less than 1, then it's going to be a vertical compression. Same thing with this other one. When I say greater than 1, it's the absolute value of that number. Or in other words, ignore any negatives. What's the number all about? If the number is greater than 1, then it's going to be a vertical stretch. So if I look at number 5 now, what happens when I multiply by a negative 2? So the 2 is a number greater than 1. So that's going to make it a vertical stretch or get it narrower, right? And the negative is what's going to flip it over the x-axis or do a reflection. So if I think about what that's going to be, my vertex is going to be in the same spot. It's going to be opening down instead of opening up, but I'm going to have it skinnier than the original by a factor of 2. So it would go over 1 and down 2 instead of over 1 and down 1 when it flips over. So it's going to go something like this. It's going to get narrower and flip upside down. So I have a reflection over the x-axis and a vertical stretch by a factor of 2. So notice the factor stayed positive. The negative is what told us about our reflection. So that's the idea, is when I'm multiplying those numbers, A number bigger than 1, it's going to get narrower. A number smaller than 1, it's going to get wider. Any negative number is going to flip it over that x-axis. So that's the idea. So now putting that all together, down at the bottom here, it says to narrow the functions in order from narrowest to widest. So the idea is I understand that it's going to be narrower when I multiply by a number larger than 1. It's going to be wider if I multiply by a number less than 1. If I flip back over to Desmos, we can kind of see, here's 1/3, right? H of x equals 1/8 times x squared. Notice it's getting closer and closer. It's getting flatter and flatter. So the closer you get to 0, the flatter that's going to be, or the wider it's going to get, right? If I change these back to whole numbers, if I change this back to 3x squared, I change this guy to 8x squared, notice it's getting narrower and narrower and narrower. So the farther from 0 you get, the narrower it's getting. Closer to 0, the wider it's going to be. Farther from 0, the narrower it's going to be. So if I'm looking for narrowest to widest, narrowest would be the largest a value, and widest would be the smallest a value. And those a values are the only things that matter when I'm talking skinny or narrow. Does it matter if it's a negative? Absolutely not. All it would do is flip it upside down, but the only thing telling us if it's narrow or wide is just the number. If I add or subtract something, that's just going to move it. It's not going to make it narrow or wide. So all that I'm looking at are these numbers that are attached to the x. So a in this case is 3. A in this case is 1/2. A in this case is, invisible number. Invisible number is 1. And a in this case is 2/3. So narrowest to widest. Narrowest, again, is the largest number. So the largest one, I've got 3, I've got 1/2, I've got 1, and I've got 2/3. So largest one is going to be 3. So I've got f of x equals negative 3x squared will be the narrowest one because it's the largest number, ignoring the negative. Let's see, after that, h of x, which is just x squared minus 5, that's going to be the next largest, or now we're going to start getting smaller and smaller, right? And then I've got 1/2 and I've got 2/3. So again, I want largest to smallest. So 2/3 is bigger than 1/2. So the next one would be k of x, which is 2/3 x squared. And finally, my smallest one is g of x, which is 1/2 x squared. So narrow and wide, we don't care about negatives, we don't care about adding and subtracting. All we look at those numbers that are multiplied by x squared, ignore the negatives. Narrowest is the largest one, widest is the smallest one. I hope that helps you really understand what happens when we multiply by a negative.